Okay, let's continue. This is going to be General Chemistry Part 12 on the electronegativity concept and the bonding polarity. Now, last section we finished introduction of different compounds. Binary compound, and then within which we have ionic and covalent, different types with the bonding polarity related consideration. And then we're going through the polyatomic ions and inside a polyatomic compound formula, and end up with a discussion on the acids and the base. And I also gave the generalized format for you to identify a oxy acid or the regular basis by the generalized form, and involve metal and non-metal. Then that time we have a periodic table with the basic layout of the metal on the left and the semi-metal in the middle with the stairwell region, and then the non-metal at right up corner. Now, something we have to discuss before we get into further about chemical reaction with different compounds, because we're going to involve the charge in the end of the section. We're going to talk about reduction and the oxidation reaction, and then all involve the polarity of the compounds and where those ions come from. In order to understand that, since we already had a small involvement in the bond type, one is ionic generally, the other big group is a covalent. So let's get into the bottom of it, why we call them ionic, what is the condition for those compounds to form ionic bonding in between and inside, or the covalent bond. In order to do that, we have to introduce a concept, and introduced and then devised by an American chemist. His name is Linus Pauling, and then the turn of last century. And then he proposed there is a scale we can do the measurements for what kind of elements to form bond with what kind of elements will be ionic or covalent. It is called electronegativity. Now, before we get into this term and the definition, we try to make sure you already had an idea. When we talk about periodicity in the periodic table of elements, we already introduced each family laying from the left to the right, column by column, and then we going through the periodicity of each period of the periodic table from a metal, majority of them, very lengthy, and then through the small region of semi-metal and getting to non-metal area. Now, already mentioned, metals only forms cation by losing electrons, which during the process of chemical reaction, and then it seems to be easy to lose electron, become cation. And then most of the anion, if they interact with the metal, they normally grab the electron or steal the electrons from the metal element, from their atoms, and make them a positive charge anion or cation, and themselves, those non-metal atoms, become negatively charged anion by gaining electron. Now, we already we have named them, the losing electron from metal is called oxidized, and the gaining electron is called reduced. That's another review. We review all the time. So you are able to review with me and get a longer retention for your learned concepts, right? So if we consider all the metal on the left side of the periodic table, most cases, almost all of them form positive charge cation, and we are able to name those elements as electropositive elements. Then the upper right corner, the non-metal, we will call them electronegative elements, because most of the case, if they interact with metal elements, they will form negative charged anion. Clear? So the two categories. Now here we have, if you have the nonmetal concentrated on this corner, and Linus Pauling said, we are able to make a scale to measure their ability of attracting electrons. Did we talk about attracting electrons from metal? Yes, if you have a metal, non-metal getting close enough, now who's gaining this electron during the bonding formation? The electron is going to get close to the negative charge anion or positive charge cation. Of course, it's getting close to the elements form negative charged anion, which are those category of non-metals. So he set up the scale. Some textbooks say 4.1, most of them say 4.0 for fluorine. Fluorine is a element at the upper corner of rightmost side of the periodic table, and it has a very, very high tendency to gain one more electron. It will become what? Become a neon configuration as noble gas, right? So that is the case. So he's assigned the fluorine has a electronegativity, which is the scale for measurements to measure the ability of attracting electron to itself during the bonding formation in a molecule or in a compound formula, right? Of compound. So that's as fluorine set up the highest, the electronegativity value is 4 or 4.1, and then compare other elements to the ability of attract electron towards themselves during the bonding formation from with other elements, right, in the compound formation. And then he set up a scale to all the way to the lower left corner where the lowest scale for electronegativity, which means those elements are most electropositive. In other words, most time they tend to form a positive charged cation, so we call electropositive. And to the contrary, on the other end of the periodic table, which are fluorine, chlorine, and oxygen, right? Nitrogen, those were considered as very, very getting stronger and stronger what? Stronger electronegative. In other words, if those elements in the upper right corner and the lower left corner meet in the close range, when they form bonding through the electron clouds overlapping, we call electron orbital, electron clouds, and the electron to interactive to form a bonding to reduce the energy of the entire molecule or compound formula as a system, and that formula, compound formula, or the molecule will be more stable, can exist in nature by itself, right, spontaneously, and for a longer time. That's stability. So that's how the bonding forms. But when you form this kind of bond, because the electrons are getting close to the elements on the upper right corner in the category of non-metal area, and then that end seems to have a more negative nature because the electron is concentrated on that end, not this end. This end is losing electron and then getting less electron, so negative value is less stronger than the other side. So this end, molecule is a binary, become a slightly positive, or polarity was established during those binary ionic compounds. Now, if you understand this, now I slow enough already. So let's go back to what's the definition for electronegativity, right? So by definition, there's two actually is similar. They help each other to make the readers or the learner of chemistry understand better. So I put it here and collect both of them and put here in one sentence. All right, it says electronegativity is defined as what? Defined as the affinity of atoms. Now, affinity means what? Affinity of atoms are available for what? What kind of affinity? The affinity of atom for electrons, right? For electron, right? So what is the atoms we talk about? It can be the atom from the same element or different element from binary compound, or same elements from same element become a molecule. There's two situations, right? If the same is going to be molecule, like the hydrogen molecule, hydrogen gas molecule, H2, both are hydrogen atoms. And if you have different elements involved, they're atoms, and one may come from here is calcium, another one is chlorine. So they two are in different category of metals and non-metals, right? So they both have an ability to pull the electron towards the cell because they both are atoms. Atom have what? In the very center of atom has what? The nucleus. The nucleus has what? The nucleus contains number of protons, right? Protons, right? And then they have positive charge. They are positive charged particles. So those particles have affinity or attraction force, all right? Attractive force towards the electron. So, but when you have both have the ability to attract electron, then you have a competition, right? The competition between the atoms from the same or different elements, which they have either exactly same electronegativity for hydrogen gas, both are 2.1, they are same, exactly identical, right? Or you have hydrogen 2.1 for fluorine's 4.1. The difference between these two elements will be 2.0 as the difference of electronegativity values. Then in that case, right, all these cases, if it's more than 2, they normally form an ionic compound with a polar molecule. So the electron will be concentrated towards the fluorine instead of close to hydrogen, right? That's called hydrofluoric acid. Alright, so HF, right? But if the same, there will be the hydrogen gas molecule, H2, both the same, then the electron, right, being shared right in the middle of the two nuclei, none of either is stronger than the other, right? So they are not able to pull over towards either side, but they share equally 100%. We call 100% covalent bond. Now we're going to list down it. We're going to put down the board, and you are able to take notes or review for the future. But now I'm describing, right? Explain now. So let's go back. The electronegativity is defined as the affinity of atoms of element, right? Could it be same elements or different elements, right? The atoms are from element. For the electron, right? Shared among the electron. We're not talking about electron belong to the atom itself. We talk about the electron, right? Form a bonding. You contribute one electron, and I contribute one electron, form a single bond. The two electrons have a spin, opposite spin direction, and form a overlap of electron clouds, right? And then interactive to lower the energy of both of us before we form bonding is higher. Now form bonding is lower, more stable, become a molecule or a formula of compound, right? That's stable in nature, right? So that's the case. So they have an affinity for electron in a molecule or in a compound. Now that's one way to understand electronegativity. Another way is the electronegativity is considered as the ability of an atom in a molecule to attract shared bonding electron. Now two electron per bond. We're going to get in there in the future, but we already mentioned a couple of times. To itself. What is itself? To the atom. So in other words, we can use that hydrogen and fluorine, right? We talk about HF, F is 4.1. Here's another hydrogen, a dotted line box. Why I put hydrogen down there? You already knew. You already knew because I gave you a black-white periodic table. I deliberately put one hydrogen box on top of halogen. This is halogen family. This is noble gas, right? Helium, neon. Right here, this is neon. Now neon, why this one is blank? Well, they barely form a compound, right? They barely attract the electron from outside, from anybody else. They already self-contained, with their own electron to form a octet, which is 8 electrons outside, the utmost share of electron configuration. They are already stable enough. So that's what we call inorganic. They don't form. They don't normally form compound, but very few. When you go down for the column, you got an argon, a xenon. They have more electron. The outside electron is far away from the nucleus. The proton, their power of attraction can reach strongly, so these seem to be a little loose. When they're a little loose, the big electron clouds, right, have more electron involved. Those outskirt electron getting a little bit of a troublemaker, right? Troublesome. They are not stable. They try to do something, right, to the outside to form bonds. So that is okay. But not very many, but only very few. All right. So most of the case, we see this carbon zero because there's no need to talk about their electronegativity value for a noble gas. So now, if you have fluorine 4.1 and hydrogen 2.1 difference too, and they form very strong ionic compound and with a ionic bonding, right? A binary compound. So this case, now we understand. So now let's see how many types we are encountered, right? I said we have already encountered at least 2 types of chemical bonds so far in compounds. We introduced the last couple parts. The first one we talked about ionic bonding, right? Now we have to define the ionic bond. Now this is the part on chapter 8 or chapter 9, right? Now why I talk about this? Because when we talk about a compound, I firmly believe, if you already talk about the compound and involve some new term, new terminology, ionic, covalent, right? Partial, polar, polarity, those terms, if you don't have a previous knowledge like a chemist, right, learned chemistry me like 40-something years ago, right, and then so it's familiar with me, but not familiar with you, right? So you need get more exposure. So if you had a sound middle school and high school chemical education, which you don't, I believe you don't have too much about it. It's not that strong. So then you need more exposure because everything to you are strange, right? Everything to you is strange as hell, and you get, oh, that is over my head. I don't want to learn because I don't know about it. Now you don't know, but you are able to learn, right? That's what I'm saying. I always say you are able to learn. You're not just a visual learner. You are a learner through any ways and means you are able to learn. So you are a capable person, but you have to be dip into the position or the situation, right? Get involvement. So you got to have more exposure. That's why I'm talking about this here. In most of the mention a little bit and jump to another chapter way back. I try to connect a little further so you are able to connect much easier. Okay, that's what I try to do. So what is ionic bonding? Ionic bonding, right? Most of the textbook already mentioned briefly in one paragraph, and I'm going to detail a little bit. Ionic bonding formed between what? Between atoms of electropositive elements, which is most of the metal, and electronegative elements, which are most of our non-metals, right? And via what? Via an electron transfer process. Now, electron transfer process. Does this term sound familiar? Which part we talk about electron transfer? If you recall, if you don't, go back to part 7, part 8, or maybe part 9, part 10. You may find, oh, we learned that term a long time ago during a introduction of what? Reduction and oxidation process, right? Reduction is what? Gaining electron, and oxidation is losing electron, and if you gain electron, you become an oxidizing agent. If you lose electron, you become a reducing agent, because your electron goes somebody to reduce somebody, right? You become an agent of doing that job. We already talked about this. So in this case, what is transfer process? Means one element lose electron, and another atom of another element will gain that particular electron, or particular 2 electrons, 3 electrons, depends on the different species we talk. The species is another general term for substances, including atoms, ions, molecules, compounds, blah, blah, blah. Everything we call species. Human being, dogs, cats, all right, species, right? And so what is the process transfer? So the electron must be transferred from the electropositive elements to the more electronegative elements, right? This happened almost all the cases between the metal and non-metal, but also can be partially occurring inside compound made by metal, made by non-metals only. Now we do not call them ions, right? We call them covalent bonding molecule, covalent bonding compound. But within those formula of the compound, you are able to figure out which elements seem to be more negative. That's what we try to find the oxidation state for the chemical compound. Did we do that? We've been doing this all along. If you missed my video, go back to view or watch my video, you will see we mentioned the oxidation state. Oxidation state, some books says call it oxidation number. That's okay, but oxidation state is much better. And oxidation state inside compound. We've been doing this. We've been giving you homework, right? 5, homework 6, right? Now it's homework 8. Already sent you today, right before lunch, and then you should receive your J number email. And we all talk about these filling out the charge of the whole polyatomic ions, or filling out the oxidation state within a neutral compound formula, or find out the subscript for a compound made by such elements plus such elements. Like the one we introduced you to go canvas, right? We already said don't go canvas because that book has so many mistakes, especially the aluminum and the carbon, right? That's example cited by the author for the Open's textbook chemistry, and it says Al, right, 4C3 is an ionic compound. No, it is not. Now we are able to do this just a moment. Let's continue. Okay, so what is ionic compound? Ionic compound, the ionic bonding is the key for ionic compound, right? So what is ionic bonding? Ionic bonding is formed between atoms, we always talk about. And then the transfer process, right? The electron transfer. So what kind of bonding we form? Form a very strongly polar ionic bond. In other words, the bond, one end, it seems to lose electron to the other end of the elements. Then I'm losing electron, right? For instance, if I'm a hydrogen, I had how many electrons? Hydrogen had 1 electron. If I lost, that's my only son, right? I lost my only son, and I don't have a son anymore, right? So I lose my electron. The electron used to spin around me and protect me, and I am positively charged, right? Now it is gone, and I become naked. N-A-K-E-D, naked. What is that? Naked proton, what? Right? Because the proton for hydrogen is normally within the electron clouds of that one electron spinning so fast, you know, in the 3D, tiny 10 to what? 10 to minus 10 meter, right? That's the diameter of the atom, right? Average atom. And if the one atom of hydrogen, the average size is about the 1 angstrom. That's the 10 to minus 10. So with spinning around, so you protect the proton is not exposed to the outside. But now the electron goes to somebody else. For instance, goes to what? Goes to the chlorine, right? Become a hydrochloric acid, HCl. Then my cell, the positive proton is exposed naked to outside world, become positive end, right? So it have attraction towards the negative end, right? Anything is negative, so I attract to my body. And then the other end of the hydrochloric acid, chlorine gain 1 electron. The chlorine got 17 electron, right? It's neutral. It's atom by itself. But again, 1 more. Is that 1 more electron is going to be showing a little bit more negative nature? Of course, yes. So on the other end for HCl, hydrochloric acid, right? It's going to be showing the chlorine side, the end of a chlorine is slightly negative. So that will give you a positive on my side H and negative on the other side of chlorine. So this looked in straight line 180 degrees from hydrogen to chlorine. That straight line is on behind my back on your left for the screen is going to be slightly what? Positive. And on the other side of the linear line, HCl is going to be slightly negative or very negative. On the other side, very positive on my side. So that makes a polar ionic bonding, a single bond right here. So example here we use what? You use sodium chloride, table salt. Now table salt is a good example for you to understand a single ionic polar bond, right? Sodium, let's see if we are able to evaporate the sodium metal into the gaseous phase, become sodium gas, and then if you kick out the last electron out of the subshare of sodium atom, which is the last one outside. How many electrons sodium has? 11. right? Has 11 proton, 11 electron. So these two 11 positive, 11 negative will be neutralized, reach the what? Reach the neutrality of the atom, right? But then if you have any process, right, physical process or chemical process, both, and if you're able to kick out one electron, right, it's not going anywhere lost. It's going to go somewhere, right? Because we have what? We have called law of conservation of energy, right? Electrons and energy. Is it electron energy? Of course, we mentioned this is not first time, maybe the second or third or fourth time we talk energy. Are you charging your battery every day? Yeah, what do you charge your battery for? Charge with current, right? And then the battery charged, right? The battery charged, and then you get the power, right? The power is what? Power is energy. So charge is energy. That's exactly the same thing. So if you are able to kick that one electron out of the subshell of sodium, the sodium becomes positive charge, cation, and that electron is not going anywhere, but pick up a what? Put nearby chlorine gas, a single one chlorine gas atom in the air, if that's possible, and then it's under a certain condition, right? And then that atom of chlorine is able to pick up what? To pick up the electron from the sodium, to put into what? How many electrons chlorine has? Chlorine is number 17. All right, we already talked about it. We did not completely finish. And the first two electrons out of 17 electrons feel very close to the nucleus, spin around, and because they are both both negative charge, oppose each other, don't like each other, repel each other, so they tend to stay along the straight line 180-degree opposite. You stay there, I'll stay here, and in the middle is the nucleus with 17 protons. And then we don't interfere with each other because we don't like each other. And then that's the first two electrons we call 1s orbitals. And then the number 4, number 3, number 4 electron come in like a cone of ice cream cone, and getting more and more space, getting extending outside outward, right? So you get more space. You are able to put more electron. So the next two electron, number 3 and number 4, were able to fill in the 2s orbital. And then the number 5, number 6, those electrons were able to spin around outside 2s orbital, 2 electrons, and then get more space. They are able to free spin in their own turf. But they don't like each other, so they were extended their orientation around the nucleus, one on the X positive, one on the X negative. The other two, Y X positive and Y negative. The next two is Z positive and Z negative. We call p orbitals, right? It's 90-degree apart, right? And then for X axis, you have two electrons on either end of the coordinate, right? And so you have 6 electrons, right? Then we call px, py, pz, subscript px, py, pz. Then each one take 2 electrons. So those electrons build up. The total is number 10 now. Then the 7 electrons left over will be also doing the same thing, all right? Doing the same thing, and into the third period, and then that will be occupied 3s over 2, and then remaining 5 electrons will spin around x, y, z, but one coordinate, either x or y or z, they are identical. It's called a degenerate. They both have the same ability to take 2 electrons, but each one take 2. 3 coordinates able to take 6, but you may give them 5 because chlorine only has 5. So you have 5 electrons filled in 3 space, 3 coordinates take up to 6. You need one more to be more stable, like argon. So where the electron come from? The electron coming from the sodium. That one electron kick it out and getting close, attracted by the nucleus of what? Chlorine. And to make a chlorine gain that electron from the sodium and to make itself 18 electron. 18 electrons is what? What element is 18? Argon. What electrons are 10? Sodium loses 1 electron from 11 become 10. So 10 electrons become neon configuration, and the 17 for chlorine gain 1 electron become argon configuration. Both neon and argon are noble gas. They are more stable than the chlorine and sodium themselves. So you achieve a stability from bonding between the sodium atom and the chlorine atom. That's the single ionic compound, ionic bonding, and then make the whole system NaCl much more stable with lower energy than individually Na gas and Cl gas, as gas is not really in existing nature. So that is the bonding formation for the ionic compound. Now we continue for the covalent next time. Next section.